Okay, transferring heat. There are three basic ways to transfer heat: conduction, convection, and radiation. Okay, those weren't the tools that I wanted. Conduction, convection, radiation. My pen always likes to choose whatever it wants. It has a mind of its own. This allows us to move heat from one location to another location. Okay? Transfer heat through conduction, transfer heat through convection, transfer heat through radiation. Now, these different modes involve different microscopic processes that are going on. If we're transferring heat via conduction, it is one molecule or atom next to a neighbor which collides and transfers the kinetic energy from neighbor to neighbor. This is a very slow process in many cases. So conduction or heat transfer through conduction is generally very slow. Convection. Convection can be driven by gravity, or it doesn't necessarily have to be driven by gravity if there's an external source to make the fluid move. Usually it's gravitationally initiated, okay? This can transfer heat faster in many cases because what happens here is due to buoyancy, warmer fluid rises and cooler fluid sinks, okay? This is more of a macroscopic effect. We can actually physically see the fluid in motion. But again, this only happens if we are dealing with some type of fluid. The last is radiation. What happens with transfer of energy through radiation? Well, in this particular case, the surface is emitting electromagnetic energy, usually in the form of infrared, okay? Really, really hot things will glow at shorter wavelengths, but normal things will radiate infrared light. And this is due to the oscillations of electrons on the surface, atoms, the molecules, whatever. They give off this electromagnetic energy, and then this can propagate through space and then be reabsorbed someplace else. So when we think about what happens here on Earth, we get energy from the sun through radiation. That radiation is absorbed by the surface of the Earth, okay? Conduction will conduct some of this heat into the Earth, some of the heat to the air around, and then convection can circulate it, right? So again, conduction, the transfer is really on a microscopic scale. The rate of conduction really depends on what type of material we have. Molecules vibrate about their equilibrium positions. The particles nearest this heating coil will have the most kinetic energy, the largest amplitudes. They'll transfer this to their neighbors, and eventually energy transfers through the entire system. The one thing that conduction does, besides transferring kinetic energy between molecule and molecule, is if we actually have a metal, metals have an advantage that insulators don't. Metals have free electrons, okay? The electrons are all over the place. And they can have kinetic energy. So if we have an insulator, the heat has to go from one to the next, to the next, to the next. It's a slow process. Every neighbor will transfer energy to the next neighbor, and that can take a long time. But if the electrons are free, they can take some of the kinetic energy from the cold end of a system to the hot end of the system, and that's why metals are better conductors than most insulators. Okay? So again, in general, metals are good thermal conductors. Also see they're good electrical conductors because again, there's a large number of electrons that are relatively free to move about the metal, and they can transport energy from the hot end to the cold end. Now, here's an equation that shows the power that takes place when we have conduction. All right? Power is in watts. How many joules per second? The amount of power is equal to the rate at which heat is transferred over a given amount of time. Okay? Now, what does this depend on? Well, it depends on, first of all, the type of material. K is the thermal coefficient of heat transfer. Okay? Metals have a very high K, insulators have a very poor K. A represents the cross-sectional area. So if I have a slab of material, okay, the more area it has, the more length and width it has, okay, the more atoms I have in the direction of heat flow to transfer that heat from the hot surface to the cold surface, right? Obviously, the greater the difference in temperature, the more heat that's going to be transferred at a given rate. And then finally, the distance that or thickness that it has to travel through a material is also going to affect how quickly the heat transfers. Okay? So that is the equation for heat transfer. Again, it is measured in watts. So power is equal to the thermal conductivity, cross-sectional area, the difference in temperature between the hot and the cold surface, and finally, the thickness of the material. So what this tells me is, if I want to conduct heat very, very quickly, okay, I want a good thermal conductivity. I want lots of surface area to do this. I want a large change in temperature between the hot surface and the cold surface. And I don't want a very thick material. In many cases, I want to hamper the transfer of heat flow, okay? I want to decrease this power. In that case, I want a low thermal conductivity. I want very little area. I don't want a large difference in temperature. And most of all, I want a tremendous amount of thickness to insulate, okay? So let's look at different materials. And the first thing that we notice is, yeah, this makes sense. Metals are good thermal conductors. These are all metals right up here. Notice their thermal conductivity in joules per second, meters, degrees Celsius. They're all in the 10s and the 100s, okay? And the best thermal conductor, by the way, is actually silver. Okay, silver is a very good conductor. It's also a good electrical conductor, but silver is expensive. So generally we use copper or copper alloys for good thermal conductivity or good electrical conductivity. Then we look at some other materials. Ice, stone, concrete, glass, brick, water, all have moderate amounts of thermal conductivity. And then the worst thermal conductors are snow, soil, wood, and really poor, really good insulators. It's fiberglass insulation and air. The problem with air, however, we got to point that out. The problem we have with air is with air, we can get convection because the air is very poor in conduction. So convection will transfer that energy. Okay. So again, power, oops, I don't know why it shows that. Power is equal to the thermal conductivity times the difference in temperature, the cross-sectional area, difference in temperature, and then also the thickness. If we take, let me change that D, by the way. Change that D to an L, L being the thickness. If we wanted to take into account the insulating properties of something, we want K divided by L to be small. Now, the inverse of that is what we call the R value. R is equal to the inverse of K over L, or L over K. You'll see this in a lot of insulation, asking, what is the R value for this insulation? Well, what they're trying to do here is ask the question in terms of what is going to give me the lowest power transfer? What is going to give me the least amount of energy per unit time as I'm going from the hot area to the cold area, okay? Again, if you're heating a house, the interior is going to be warm, the exterior is going to be cold, and the greater the temperature difference, the more power you're going to lose to the outside. We want to insulate that home. We want to, again, make this value very small. So use something with a low thermal conductivity and something fairly thick to inhibit the transfer of energy. And again, that is R value. So when you insulate a house, you're trying to maximize your R value, which is really how much have we thermally isolated the interior of a building from the exterior, okay? And we can see what some of the effectiveness is for this different material. Hardwood siding, not great, okay? You're not gonna want a house that just has hardwood siding trying to keep the heat in. Same thing with wood shingles. Brick's a little bit better in terms of R value, but again, brick has very similar thermal properties as stone and concrete. It conducts heat pretty effectively. Concrete block, again, pretty conductive for heat, so not a great R value. But here we start getting into real insulating materials. Styrofoam, nice insulating material, okay? In fact, we use it in coffee cups because it prevents the hot coffee from transferring heat to our hands where it can burn us. But 3.5 inches of fiberglass insulation, 6 inches of fiberglass insulation, you can tell as you get thicker and thicker, you get much better R value, much better insulating properties. And here's some other things. There's fiberglass board, cellulose. Oh, by the way, windows are terrible for keeping the heat in. Drywall, not good. And again, sheathing is basically just oriented strand board, not great. So again, in the wintertime, when temperatures are cold, you want to rely on a material like fiberglass insulation to block the transfer of heat. And here are different R values that are recommended for different parts of the country. I'm up here, by the way. Okay, so different parts of the house you want at different levels. Like attic, you want a tremendous amount of insulation. R49, you need multiple layers of fiberglass insulation to get that up to R49. Remember, even 6 inches was only giving you about an R of 10. Cathedral ceilings, walls, R18, the floor, R25. And again, down in New Jersey, most of New Jersey is not all that different, okay? R49, R38. Pretty much the same levels, okay? So here up in the Northeast, we want, fairly well insulated structures. In other parts of the country, you really don't need that as much. In Florida, the R values are more about keeping the cold air in, the warm air out. So the R values are lower. And here is that fiberglass insulation. Fiberglass insulation is mostly nothing, okay? It's 93% air, okay? Air is a very good insulator. And to prevent the air from convecting, they blow borosilicate glass into there, okay? If you've ever handled fiberglass insulation, you know the pain and the irritation of fiberglass particles in your arm, okay? Always wear gloves, always wear protective clothing, always wear eye protection. But again, a properly insulated home can be very thermally efficient and keep the warm air in during the winter and keep the cool air from getting out during the summertime. This is a infrared picture of a house, and you can see they've done some things well and some things aren't going as well. So for instance, the roof is pretty good, okay? Blue represents almost no heat transfer, represents cool. Green is fairly cool, so the roof is keeping the heat in pretty well, okay? The walls, well, exterior walls, they're doing okay, but not as well as the roof is doing. Obviously, the worst place are these windows. That's a terrible window right there. The windows are where most of the energy is actually escaping, okay? And this shows the difficulty of getting transparent windows, which are also well insulated. The way that we try to achieve this is to use multiple panes of window, okay? Single pane glass is not up to code anymore, which means that you can't build a house with just a single pane of glass anymore. If you do it, it's not going to pass inspection up here, okay? What we do is, in creating double pane glass, we put gas in between two panes. It's actually hollow here. And because the space is so small, convection isn't really a problem. But the air acts as an insulating body. Again, air is a poor conductor of heat. Glass is a pretty good conductor of heat. So if we can put this dead space in between the glass, usually we fill it up with argon gas, so water vapor can't condense and fog up the windows. But this does much better than a single pane. You can also get triple panes. You get three different panes of glass with two spaces in between. And again, whenever we engineer a house thermally, we're always looking for different materials for different places to prevent heat loss. Good fiberglass insulation for the spaces in between walls, and multi-pane glass for windows. But actually, the fewer windows you put on a house, usually the better thermal management will have against losing energy, or one way or the other. And again, if you have multiple materials, you can just add the R value together, okay, to get the total effective R value. Maybe you have the R value of the sheathing, plus the R value of the insulation, plus the R value of the sheetrock, okay? Each individual layer is going to add to this and reduce the amount of power that we lose, because power is inversely proportional to the R value. Let's look at the energy transfer in 1 hour by conduction through a concrete wall. And just to let you know, oftentimes now they'll actually insulate foundations to prevent this transfer, okay? So we know that power is equal to energy divided by time. So we want the total heat that's transferred, okay? It's just power in watts. Watts are joules per second, times time. Here we're going to have a time of 1 hour. And that's going to be equal to Ka, the difference in temperature over the thickness of the concrete wall, and then again, times the time, okay? Okay, so find the energy transferred in 1 hour through this. So our thermal conductivity of concrete is 1.3 watts per meter degrees Celsius. We have a 7.3, that should be squared, okay? 2 times 3.65 is 7.3. The difference between outside and inside is 15 degrees Celsius. The wall is 20 centimeters thick. And in 1 hour, that's 3,600 seconds. Well, that's equal to quite a bit of energy, okay? Just through that small part of the foundation, we lose 2.6 times 10 to the 6 joules. And again, that's why insulating is so important, okay? Convection, we don't really have an equation for this. Convection, again, is energy transferred through the movement of a substance. Natural conduction will happen due to a difference in buoyancy. Warm fluids rise, cooler fluids sink. We can also force convection with a fan. But most of the examples that we're going to look at here are just natural convection. All you need to do is hold your hand above a flame and you can feel the hot gases rising due to the buoyancy, okay? Density of the air decreases as it's heated, it rises. And this really is how we generate our convection, okay? The warm air rises, cools off, becomes more dense, sinks, and then is reheated and rises again. So around a radiator, these radiators are actually designed with these fins to maximize the surface area, the conduction with the air, and they will convect warm air upward, okay, as the cooler air is pulled down from below. All right. And again, you want to set up your room so that the radiator can work with other elements. Here we can see the warm air is going to rise from the radiator. It's going to cool, become more dense. This can be enhanced by the location of a window because we know windows aren't very good at keeping energy in the house. And then again, it's reheated as it goes back through here. So again, setting up a room, don't put your heaters all over the room. If you have these radiator type heaters, you won't want to place them in one part of the room and let convection mix the air. We also get convection in lakes and ponds. When it's very cold in the winter, the bottom of the pond stays around 4 degrees Celsius. If the pond's deep enough, even during the summer, it'll stay fairly cold at the bottom of the lake. But what happens is, in the fall and the spring, due to convection, the pond or the lake will actually turn over, okay? In the summer, the top of the pond is warmer. So as fall comes, it cools down, the water cools to 4 degrees, and that sinks to the bottom where it mixes with the lower water and overturns the pond. In the spring, the whole thing changes over again. The surface goes from 0 degrees to 4 degrees. Again, the 4-degree water sinks and displaces the other water, and the pond turns over once again. Convection also powers storms. As we said, the warm, moist air evaporates from water, or it evaporates from the surface, goes high into the atmosphere, carrying energy with it, okay? But as it goes higher, the pressure drops. The gas expands and it cools, and this causes the air to become denser. Now, even before it starts raining, the cooler air heads downward and produces convection. The rain actually creates additional mass, which pulls the cool air downward. And that's whenever you come across a thunderstorm during the summer, all of a sudden you feel this sudden drop in temperature. That's a convective mixing that is created by a storm. Now, convection actually drives most of our weather in the atmosphere. If our Earth did not spin, one side would be very hot and the other side would be very cold, but we'd also have a single convection cell. The air at the equator would rise, flow to the poles where it would sink after it cooled down, and then go back to the equator where it would warm up again. One big northern convection cell, one big southern convection cell. But because of the Coriolis force, it actually breaks into 3 convection cells. One in the tropics, one at our latitude, and one in the polar region, okay? In the mid-latitudes, we generally get our weather from the west. Why? Because at the mid-latitudes, the air actually wants to flow southward, okay? But because we spin, the Coriolis effect redirects us from the northwest to the southeast, okay? So watch the weather. It's always coming from the west in our location. That's not true if you live in Florida. The tropical storms will start from the east and head west. And again, that's because they're under a tropical cell, convection cell, whereas we are under a mid-latitude cell. And convection, we can see that here. Here's the tropical cell, okay? Here's the mid-latitude cell, and then there's a polar cell up here. Convection also drives the ocean currents. Now, this is a little more complicated. Yes, it's due to a difference in density, but temperature is one of the factors that changes the density of the ocean water, but it's also salinity, okay? So what happens here is the warm Gulf Stream, let me use a different color. The warm Gulf Stream takes tropical water, okay? Goes up past North Carolina. That's why North Carolina is much warmer than us. But it sort of bypasses us as it heads out to Europe, making Europe much warmer than it should be. It then goes up to the Arctic where it cools, and then it sinks, and this deep cooling current will then head back down, okay? Now, this global conveyor belt constantly transfers heat from the warmer regions to the cooler regions, equalizing the ocean temperatures more than they would be otherwise. And you can actually see the Gulf Stream right here. See, coming up here, heading out here. Here's Cape Hatteras, by the way. And notice we're up here. Completely bypasses us. And that's why Spain, even though it's at the same latitude as New Jersey, Spain is considerably warmer due to this Gulf Stream. Convection also drives plate tectonics. The heat from the core due to radioactive decay will make the core much warmer than the mantle. Heats the interface between the mantle and the core, and this causes mantle plumes. Now, we're not quite sure how complete these cells really are. First of all, the mantle is technically a solid, okay? It has some fluid-like properties, but the mantle will rise in some locations, and it will sink and pull the crust down in other locations. So where it rises, we get divergent faults, we get mid-oceanic ridges. Where it sinks, we get subduction zones or convergent faults. Okay. On to practical matters. Not that ocean currents and plate tectonics aren't practical, but one thing that we need to do when we're active in the winter is properly manage our heat. You know, when things are very cold out and you're inactive, you want to retain as much body heat as possible. If you're active, such as playing in a sport, or let's say shoveling a lot of snow, you will not only generate a lot of heat, but you'll also generate a lot of perspiration, water. So one of the big problems that happens is that you layer up to keep this heat in, you work out, all this water soaks your clothing from sweating, and then you're not as active, and now the water conducts more heat, okay? Your clothing's wet clothing conducts heat very efficiently. It's not good insulation. So manufacturers have figured out ways to decrease or manage heat and manage moisture by using things like this winter fleece, okay? What this allows to have happen is it wicks the moisture away from your body so it can make it to the outside and evaporate. But it also has quite a bit of insulating space within it. So it keeps the heat from escaping, okay, while it allows the moisture to get out. So if the water's not building up close to your body, you're not changing the insulating properties of your clothing. You're keeping the insulating properties high. So this high-tech clothing can go a long way to keeping you comfortable when exercising out in cold weather. Okay, radiation does not require physical contact like convection and conduction do. Radiation obeys something called Stephan's law. And this depends on a few different things about the object. Now, we're going to talk about something called a black body. And a black body is, as its name implies, is a very dark surfaced object which absorbs light very easily. But in nature, a lot of times we get symmetry. You know, what one thing does very well in one direction does very well in the reverse direction. So what we know about a black body is not only does it absorb light very easily, okay, it also emits light very easily, okay? It emits thermal energy, usually in the form of infrared, okay? If we compare that to a highly reflective object, highly reflective objects are very poor black bodies. Not only do they, let me get the correct here, not only do they reflect the incoming radiation very well, they also don't give off very much radiation, okay? So that's sort of a weird thing about nature. You know, if you wear dark clothing in the summertime, you're gonna get warm much faster in the sun. If you walk on hot asphalt in the summertime, well, I've already told you, it's hot asphalt. When we used to go down the beach, we try to walk on the white lines that were painted on the asphalt to try to not burn our feet. Again, darker objects absorb and emit radiation very, very easily. So again, an example of thermal radiation, all you need to do is stand near a campfire. Yes, it'll heat the air around the campfire, but really, most of the benefit you get from a wood fire is from the hot coals giving off thermal radiation. You have no physical contact, but yet it is warming you, okay? All dense objects give off some thermal energy in the form of electromagnetic radiation. We glow around 10 microns, okay? 10 microns, and that's in the infrared. In fact, pit vipers hunt mammals because mammals are homeotherms. They regulate their temperature and glow at this wavelength, which the pit vipers have little pits on their faces to track down. Now, they're not normally hunting us, but they can see you even in the dark using these pits. They usually hunt rodents with it. All right. We call the process of glowing due to thermal radiation incandescence, okay? So for instance, here's some hot coals here. They're glowing orangish red because their temperature is around 1,000 degrees Celsius, okay? Incandescent bulbs glow mainly in the infrared. That's why they're so inefficient, but also give off sort of this whitish, yellowish glow because they're about 2,000 degrees Celsius, okay? So incandescence is another term for giving off black body radiation. Now, measuring temperature is something that is very easy to do if we know the wavelength that the object is giving off, okay? We use it in astronomy. We use it in the everyday world. Little ear thermometers or the forehead thermometers, they're looking at the infrared that you're giving off, okay? So again, hot objects give off thermal radiation, and it tends that they give off in shorter wavelengths, okay? Human beings around 10 micrometers, that's where we peak. All right, those hot coals, they peak around 1 micron or 1 micrometer, but they give off enough in the red and orange, which is closer to about 0.5 micron, that we can see things glowing. Our sun, it gives off a peak radiation somewhere around 0.5 micron, okay? So humans to hot coals, to the surface of the sun, notice the wavelength is getting shorter and shorter. Now, if you've ever heard the term white hot, that is an object that's about the temperature of the sun that's giving off all colors of the spectrum. White is all colors, okay? It's red, it's orange, it's yellow, it's green, blue, and violet. It's all colors of the spectrum. And if something is red hot, it's not quite as hot. Red hot, oops, come on, stop. Red hot, it's giving off radiation mainly in this part of the spectrum, okay? But if something is white hot, those wavelengths have shifted even further where they're peaking in the yellow part of the spectrum, but yet covering all parts of the spectrum. The hottest things, like blue stars, like welding tools, they are so hot that they give off sort of a bluish glow, and they're dangerous because they give off a lot of ultraviolet light. And we notice what's happening here. As things get hotter, okay, the wavelength is getting shorter and shorter and shifting to the blue part of the spectrum. Now you're like, well, why do we associate red with high temperatures? Why is red hot considered to be, why is red considered to be a hot color where blue is often associated with a cold color? Well, that's because most things never get up to being blue hot, okay? They're either red hot or in rare cases, white hot, all right? Blue we normally associate with things like water, ice, and, you know, so when you talk about art and the cool colors, that's why blue has that association, okay? But in physics, actually something that's glowing blue is going to be really, really hot. So let's take a look at different things, all right? Just a review of the electromagnetic spectrum. Radio waves are the longest frequency. Microwaves are the next longest, then infrared, then visible, UV, and then X-rays, and then gamma rays, okay? Short wavelength, long wavelength. Okay, the coldest object in the universe, one of the coldest objects, is probably the universe itself. It has a temperature of only 2 degrees Kelvin, 2 degrees above absolute zero. So when we want to study the microwave background radiation from the beginning of the universe, we actually look at long wavelengths of the spectrum, the microwave part, okay? As things get warmer and warmer, like human beings, we glow in the infrared, and planets. If we took an infrared picture of a planet, it would also glow in the infrared, okay? Going even higher, in the visible part of the spectrum, we have the sun. The sun's corona glows in the ultraviolet, and the most extreme objects will glow in the X-ray and the gamma ray part of the spectrum. Okay? And again, what's that little ear thermometer doing? It's looking at the infrared coming from your ear and converting that into a temperature. So this is a look at, it's a logarithmic scale, folks. So on this vertical axis here, we're going by log base 10, powers of 10. You know, here is 10 to the 0, 10 to the 2, 10 to the 4, 10 to the 6, 10 to the 8, 10 to the 10, 10 to the 12. It's all relative intensity. So it's going up by powers of 10. On this scale, we also have powers of 10. We're talking about wavelength in microns. Okay. Let's look at a human being. Human being. We are at 300 degrees Kelvin. So notice where we peak on this little scale right here. Okay. Our peak intensity is, again, around 10 microns. That's why rattlesnakes are able to hunt mammals so well. That's where we glow. That's where they've evolved their little pits to hunt. Okay? Now, the red hot coals, they're quite a bit hotter than we are. They peak right there. Okay? So although they peak, you had a couple microns, okay, we can see that there's a little bit of visible light that they give off too. Thus, they appear to be red hot because most of the light they're giving off is red. Now we get up to the incandescent lamp, okay? The incandescent lamp peaks again in the infrared. So if you're buying an incandescent lamp, look at this. You're putting out energy mainly in the infrared. You can't even see the light. Incandescent lamps are great infrared producers. They're great heat producers, but they don't produce very much visible light that we can see. And that's why most incandescent lamps have been replaced with LEDs, much more efficient. All right. And then we get to the sun. Sun peaks right around the yellow. We call it a yellow star, even though it appears to be white. But you can see it gives off mainly all parts of the spectrum pretty equally. Okay? So as things get hotter, not only does the wavelength shift to shorter wavelengths, wavelength of light becomes shorter and shorter. Okay? The intensity actually becomes greater and greater. And again, if we look at our sun in the ultraviolet, we can see that the corona is what's giving off most of the ultraviolet light. If we look at things like black holes and supernova remnants, at 1,000,000 degrees Kelvin, they give off mostly X-rays. Okay? How do you find a black hole? Black holes are black. They don't give off radiation. But the infalling material heats up to millions of degrees, so they glow in the X-ray. Now, the most violent explosions in the universe are called gamma ray bursts. They involve the merger of two neutron stars, like we see in this picture right here, or the explosion of a very, very massive star. These temperatures can be in the billions or trillions of degrees Kelvin. So, of course, that corresponds to the shortest wavelengths of all. Okay, let's look at the important thing. Here is the important thing. The Stefan Boltzmann Law states how much power, how much thermal power an object will give off, okay, based on its properties, okay? First of all, we've got this little constant right here, right? This is our Boltzmann constant. It's the same for everything. So sigma is just a constant, just like 9.8 meters per second squared is a constant, just like, oh gosh, I can't remember what it is. I'll use Avogadro's number as a constant, 6.022 times 10 to the 23rd. Constant, constant, constant. Okay, what else do we have? Surface area. The more surface area something has, the more surface it has to glow, okay? Now, here is something that's a little bit hard to comprehend. E. E is called emissivity. If something is completely reflective, the emissivity is 0. So it actually, if we had a perfectly reflective body, which is physically impossible, it would actually radiate no energy. If it were a perfect black body, which is also impossible, it would be a 1. So all these values are somewhere between 0 and 1. Okay? And then finally, look at this. It goes by temperature to the 4th law. So if I took something, and let's say it was at 300 degrees Kelvin, nearly room temperature, and I heated it up to 600 degrees Kelvin, okay? I made the temperature twice as big. 2 to the 4 is 16. It would glow with 16 times more radiation. And again, T is in Kelvin, not Celsius. Otherwise, you'll get some weird results. Okay. The net power, if it's surrounding in a warm environment, the previous case would be if something were in a vacuum and there's no other sources of radiation around, we would get that. The net energy absorption and emission is T to the 4th, which is the temperature of the object raised to the 4th power, minus T0 to the 4th, or T naught to the 4th, which is the environment. Okay? So if you're warmer than the environment, you lose energy. If your environment's warmer than you gain energy. Okay? Positive power means that you're losing energy, you're radiating into space. A negative power means that the power is coming into you. If you are at the same temperature as your environment, the difference here is 0, and there would be no net power exchange. So again, ideal absorbers would be an emissivity of 1. Nothing's perfectly black, but actually they came up with a very interesting coating that comes very close to a perfect black body. But again, this would be something that absorbs energy very, very efficiently, but also radiates energy very efficiently. Something's perfectly reflected, the emissivity would be 0. And we sometimes see this. Did you ever see those reflective blankets that they'll put on people when they're rescuing them? The reason why they do that is these blankets don't allow any radiation of energy, but they also reflect any of the infrared from the person who's being rescued back onto their body, because radiating energy into the environment, especially if it's cold, is one of the biggest places that you lose energy. So again, applications of radiation, black fabric, they're good absorbers, but they're also good radiators. Okay? So if you want to be warm in the sunshine, you wear black. And actually, if you want to keep warm at night, lighter clothing will actually cool off slower than black clothing. And white fabric's a better reflector, obviously. And again, you can actually measure the amount of energy that an object is giving off through thermal imaging. This just simply looks at the infrared energy that's being given off. This is a neat device that's been around for quite a long time. It's called a Thermos. They used to make these all with glass, so they were easy to break. Now they're making them more with stainless steel. It's called a Dewar flask, a Thermos bottle. The Thermos is actually trademarked. But what they do is they take this glass, double wall, or stainless steel. They'll make reflective surfaces on both. And because the emissivity is pretty close to zero, we can't have thermal radiation coming in or going out of the liquid that's inside. Because it's a vacuum, there's no conduction or convection. So this thermos or this Dewar flask is very efficient at insulating or preventing the transfer of energy. Okay? A lot of times we'll use this to actually carry cryogenic fluids. But again, using one of these, you can keep your coffee warm, okay, your soup warm during the summer, or keep during the winter, or keep a cold drink cold during the summertime. Okay? Again, vacuum, no conduction or convection because there's nothing there to transfer the heat. No radiation because with the emissivity pretty close to zero, no thermal radiation is transferred.